Okay. So, I mean, we have problems like, didn't we have problems like this before, like in the group work? So prove that it's impossible for phi of n to equal certain numbers, 2 or 6, or I forget which number we looked at. Phi of n always had to be even. That was one of the things we proved. So there's some old group work about this.
Do we have a formula for phi?
Yeah, exactly. You really just want to write down the formula for phi of n, right? So and in order to do that, what you really need is the factorization of n. So let me just write out a hypothetical factorization of n into distinct prime powers. Each prime power is greater than or equal to 1. So k sub I is greater than or equal to 1. Okay. And then the point is that then phi of n is, of course, respecting multiplication. So it's phi of p1 to the k1, phi of p2 to the k2, etc. Phi of pr to the kr. And then you can just use that subtraction trick. So we're asking how many numbers are relatively prime to p1 to the k1. So what we do is we take all of the numbers up from 1 up to p1 to the k1, and we subtract out the violations, which are the numbers that have a common factor of p1 in them, and that's just every pth number. So you're basically subtracting p1 to the k1 minus 1. So like, for example, phi of 25 is 25 minus 5. Okay. Every fifth number has to be subtracted out. So take all the numbers from 1 to 25. Which ones are not relatively prime to 25? Well, they would be 5, 10, 15, 20, and 25. That's 5 numbers, so you're taking those out, right? So actually, this is a little lemma, or possibly a theorem, I can't remember, from chapter 7, right? Okay, so you just do this for each of your primes. Okay, and you just go all the way along. So then what you want to do after that is basically factor this thing down. So p1 to the k1 minus 1 times p1 minus 1 times p2 to the k2 minus 1 times p2 minus 1 times, and so on, p3 to the k3 minus 1, p3 minus 1, etc. And these are all distinct primes. So this is really the formula you want to look at. And you're setting this thing equal to 4. Okay? So my advice on how to work with this is to first figure out how big could your primes even be. Like, what's the largest prime that even has a chance of being allowed on the left side in that box?
2 or 3.
2 or 3? Anything larger than that work?
5.
5. Could you have a 7 on the left? Could 7 be one of your primes?
Yeah. Wait. No. No.
If it were, you'd have already a factor of 6. It's already too big to equal 4, right? So the only primes that are even possible are 2, 3, and 5. Let's suppose, so I think it's best, so no prime can exceed 5 in the factorization of n. Okay, so it can't be a factor of 5 here. Yeah.
In the context of the problem, we're doing n as p minus 1.
Right, we can use that as well. So that's going to eliminate some things as well, but I'm not using that quite yet. Just trying to work with the general n right here. Okay, so far so good? I did one of these in the review session for the second test, and it kind of turned into a mess, so I'm trying to redeem myself this time. I hope this goes better, because this was a little tricky last time. So, and I remember it was great, because the camera had turned off, so nobody had any evidence of it. But I think it's running now, so I better get it right. Okay, so we don't have any primes that are bigger than 5. So I would suggest trying to start by working with what are the bigger primes that are allowed. So suppose that 5 was a prime. Suppose you did have a factor of 5 in there. If you did, then you've used up on the left side, you've already got 4 right here. So this power has to be a 1, because if it was more than that, then you'd have the factor of 5 in there. It'd be way too big. So if there's a 5 in the problem, then it has to be raised to the first power. Okay? So actually that gives you one choice of what n could be. N could be 5. Okay? And it is true. Phi of 5, if you think about what phi of 5 is, it's 4. And how many numbers less than 5 are relatively prime to 5? Well, 1 is, 2 is, 3 is, and 4 is. 4 numbers. So this is certainly one answer. Is there any other way that we could have 5 as one of our primes?
Yes.
So, in other words, this is a solution where you just have one single prime. Could you also, with the same number, have a second prime?
Two.
Yeah, if I have another prime here, it can work, because if the prime is 2, 2 minus 1 is just 1, right? And as long as this exponent comes back down to 0, in other words, k2 is equal to 1, it'll work. So you can also use this number, and that number is 10. So that would be n equal to 10. You see that? So it's really just, what is it? It's 5 to the 0 times 5 minus 1 times 2 to the 0 times 2 minus 1. That is 4. That does multiply out to become 4. So that gives us a couple of options. So far so good? Is there any other way to do it with 5 as a prime? You can't have any other prime bigger than 2, because you'd be getting factors of 3 minus 1 or 5 minus 1, or it'd be too much on the left side.
And that first answer isn't possible, right? Because that would imply that p minus 1 is 5.
Right. So we would be putting this to be 5, and then p would have to be 6, which is not. So you're right. We are ultimately going to cross off the first one, but we're not going to cross off the second one. Actually, the second one's going to give us a prime that does work. But I'll come back to that. So I just want to get my whole list here. So what else could happen? Let's suppose that 5 is not a prime that is in this factorization of n. So what other prime could be a factor in here? 3. Okay, so suppose we have 3. P1 equals 3. So then I'm going to get my factor. If P1 is 3, then this is 2 already. And can I have a factor of 3 here? No, because 4 doesn't have any factors of 3 in it. So this would have to be what exponent? Well, it'd have to be, K1 would have to be 1, right? So that when I subtracted 1, it came down to the 0 power. Okay, so we have that. Now that alone doesn't do it though, right? Because this is this is just 3 to the first. You subtract 1, you just get 2. So you have to have another prime. What other prime is there? 2, right? Okay, so you have to have a second prime, P2, which is 2. And if you have 2 as another prime, 2 minus 1 doesn't help you. So you better have an exponent here that is big enough that you get a factor of 2 out of this, which is 2, exactly. So K2 has to equal 2. That's exactly right. So this is another example of a number. What is n for this case?
12.
3 to the first, right? This is 3 to the first times 2 squared is 12, right? Okay, so 12 is an option.
But that's 2.
That works. Phi of 12 is actually 4. The roots, or the relatively prime numbers are 1, 5, 7, and 11.
Oh.
So, okay. Is there anything else we can have?
Not with 3.
Not with 3?
No.
Yeah, I don't think so. Not with 3. So the only other thing we haven't looked at is, well, what if we just had only the prime 2? Is that possible? So if P1 is 2 and it's my only prime, then I've just got to make sure that this exponent is big enough to give me 2 squared. So K1 would be 3. So P1 is 2, K1 is 3, that would give me n equal to 8. So the numbers that can go in here, going back to the problem now, the numbers that can go in here that will have a phi value of 4 would be 5, 10, 12, or 8. 10, 12, or 8, and that means that P would have to be one more than each of those, which would be 6, 11, 13, or 9. These are the only possibilities. Then of course they're not all prime. So we now throw away these two, and there are only 2 prime numbers that have exactly 4 primitive roots. Oh, I'm going to find all 4 of the primitive roots for one of the primes. I don't have to do it for both of them. I think I can just get away with one of them. Give you the idea here. Okay, so let's just, which of these 2 primes do you guys like better? 11? I do too. The smaller the better. Good. Okay. And so phi of 11 is 10. So can somebody give me an element that has order 10?
2.
2. Sounds good to me. I mean, 2 to the 5th isn't even back to 1 yet, right? 2 to the 5th is 32, which is the same as -1. So this is a primitive root. Okay, so then my only other question is, how do I get all of the other primitive roots?
Raise them to the powers that are relatively prime to 12.
That's right. So the GCD of
10.
H with phi of
10. Sorry.
yeah, that's right. With the powers that you want to use have to be relatively prime to phi of your modulus, which is 11. So then phi of that is 10. Okay, so in other words, it's going to be r to the 1st, r to the 3rd, r to the 7th, and r to the 9th. These are the numbers.
Did you mean equals 1?
Equals 1. The
Yeah.
GC.
Sorry. Thank you. Yeah, so you've got 4 things to calculate. So what are the values that you're going to get? If I think of this as a set of values, it's going to be 2 to the 1st, which is 2. 2 cubed, which is 8. What is 2 to the 7th?
7.
Well, of course we already knew that 2 to the 5th was -1, so it's just -4, which in Mod 11 is the same as 7. Mod 11. And then multiply this by 2 more factors of 2 to get up to r to the 9th. So 7 times 4 is 28. In the world of Mod 11, of course that's the same as 22, it'd be 6. That's the ones. So these are your primitive roots of 11. Primitive roots of 11. Okay. Let me just did that, 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 did that. You guys are hanging in there pretty good. I'm trying to think. I'm going to do one of the problems from the group work that's a short one. I'm just going to do it with you because it's important enough that I'd like you to see it. And then I'm going to let you just do the rest of the group work on your own, in the next couple of days. And then I'm going to ask you if you have any, I do have one more other problem that, actually I have a couple more problems I haven't done that are on the sheet. I could either do them or not do them, kind of depends on how you guys are feeling. But I do want to do at least this one. So here is one more, and this is number 8. And so this is off of the group work, so there is already a solution typed up for this thing. Okay, that's already on the internet. It says, prove that every odd perfect number, and there's so many of those that we know about, prove that every odd perfect number is a sum of 2 squares.
It's group work number what?
This is off of group work number 12. The very, very last group work of the whole entire semester. So, If you had an odd perfect number, you want to prove that it's a sum of two squares. I like the problem because it ties together two seemingly different things that we talked about. It talks about perfect numbers, odd perfect numbers, but it also talks about sums of two squares. So remind me again, how do I decide if a number is expressible as a sum of two squares?
Or an odd number of 4k plus 3.
Right, if I look at the prime factorization of the number, right, of course it's odd, so they will all be 4k plus 1 or 4k plus 3. Those are the only kind of primes there are. And if there are an odd number of primes of the 4k, if there exists a prime of the 4k plus 3 variety that occurs an odd number of times, then it won't be expressible as a sum of two squares, otherwise it will. Right? So that's kind of the criteria here. So, anybody know anything about odd perfect numbers?
We have a theorem.
Is there any form?
Yeah, what form do the odd perfect numbers have?
That one theorem?
P times P to the k
If n is an odd perfect number, then this is by, let me get the correct result here.
Oh, you're writing on that board again.
Oh, shoot.
Move it, there you go.
Derek's on the ball here. Okay, great, thank you. Sorry, I don't know why I'm over here, but, all right, so if this is the case, then here's the main thing that you want to remember is that there has to be at least one prime that is raised to a power, so P1 to the K1. Then there'll be a bunch of other primes which are all raised to even powers. This is one of the theorems in the list of theorems to learn, actually. PR to the 2JR. So for an odd perfect number, you have a representation that is like that, and the PIs are obviously all odd distinct primes, but with specifically P1 congruent to K1 congruent to 1 mod 4. And then all the other primes can be sort of like whatever. They can just be anything.
Oh. So we're already almost done.
Yeah, this is a very short problem. So actually, another way to say it is, n is P1 to the K1 times a perfect square, basically, where P1 does not divide M, and P1 is congruent to K1 is congruent to 1 mod 4. So what did we say? In order for a number to be representable as a sum of two squares, any primes of the 4k plus 3 variety have to occur an even number of times. Well, look at this factorization. Here's a prime, but it's not of the 4k plus 3 variety, so I don't want to think about it. Any primes that are of the 4k plus 3 variety are over here inside of the M part, and are therefore being squared. Or you can just look back to here. I don't know which form the P2 through PR are in. I know that P1 is of the 4k plus 1 variety. The rest of these primes, doesn't matter which form they're in, they occur an even number of times, right? In fact, you could even say this is already just your M squared. You're trying to represent n as a sum of two squares. Well, here's a perfect square right here, and you just have to represent this one as a sum of two squares, and you know that you can do that. So you just represent this as like a squared plus b squared. So write P1 to the K1 as a squared plus b squared. We know we can do that. Okay, that's basically theorem 13.3 again, that we were talking about earlier. So now n is just a squared plus b squared times m squared, which just means it's am squared plus bm squared.
We wouldn't have to do that, right? To prove,
No.
to do this proof,
say it in words.
By the theorem.
Yeah. Yeah, this is just explicitly showing you how you could break it down. Yeah, do you have a question?
Yeah, the theorem says that any power of a prime can be expressible as a sum of two primes, or what does theorem 13.3 say?
Well, this is a prime of the form 4k plus 1, and it's being raised, so the factorization of this, this is the prime factorization of itself already, and there are no factors of the form 4k plus 3.
Okay,
How do we decide if a number is expressible as a sum of two squares?
if it has
We
no,
prime factorize it, and we ask ourselves, are there primes of the form 4k plus 3? If so, they cannot occur an odd, they have to occur an even number of times. But the point is, this number has no primes of the form 4k plus 3 at all, so we don't even have to think about it. We know that this number, now, it's not saying that it's easy to write down what A and B are, but we're saying we do know they exist, and so we know this is possible, and then just feed it in. So that's just off of this group work. I just thought I would show that to you. Okay. The rest of that group work I'll just let you look at on your own. Maybe not quite as critical. Just some fun problems. Do you guys have you had enough? Do you want to? Or, I mean, I have a couple more problems on the sheet here. I'm happy to go over them. But I also want to respect your time
What
and
do they
your
involve?
plans and all that stuff. Pardon?
what do the plans, what do the problems involve? Plans?
You want to? Okay, I'll tell you what there are two problems on the sheet that I haven't done. I'll write down what they are, and then you guys can tell me whether you think you can handle them on your own or want to handle them on your own. I'm happy to do them. I have so much more energy right now than I ever thought I was going to have after this many
The
hours.
Coca-Cola.
But I'm still going strong.
It's probably one of the original.
Here they are. So there's two more what
Number
numbers are we
9.
on?
9.
9. So 9 and 10. Here they are. Number 9 is just compute 12,111,009 to the 8765 power mod 4321.
What?
That's a problem. And 4321 is not a problem. But I could give you the factorization. Okay. And then the other one is this one. For what primes P, I guess greater than or equal to 7, as it turns out, is the Legendre symbol of 15 in mod P equal to 1. Of course, it's either 1 or negative 1. And so the question is, for which primes is it 1 and for which ones is it negative 1? So both of these problems would take a little bit of time, but I'm happy to stay and talk about it. Yeah, Fran?
There's also a fewer problem. I don't know.
Oh, you know what? There is. Okay, you're right. There's a third problem I didn't do. That one is a really pretty easy one. It's just, basically a Chinese remainder theorem little example. So I might skip that one, and then people can ask me that question. So you guys aren't all running for the door.
Can you number 9?
Do you want me to do these? Talk about these at all? Please? Somebody said please? Okay, sure. Let's see if I can, well, I'll at least do the first one and then we'll see how we're doing. Basically, so now that I'm going to do the first one, let me just say on the second one. On the second one, you basically want to do this. And then you want to say, well, either these are both 1 or they're both negative 1. And then you have to figure out, well, when is this one 1 and when is it negative 1? And then when is this one 1 and when is it negative 1? And it actually gets kind of a little bit messy. You have to look at some cases, basically. So, okay, getting back to the one that's up there at the top, I'll help you out with it by telling you that 4321 factors. It is, as it turns out, 29 times 149. Okay, and I knew there was a reason I brought my calculator today. I don't know if we've been using our calculators very much. We may want to use them for this one. What would be the first thing you would maybe want to do?
Reduce 12 million, whatever, mod 432.
Reduce this thing down. Now, see, the thing is, 29 and 149 are primes. So we could compute what this thing is, mod 29, compute what it is, mod 149, and then use the CRT. Okay? So I'm going to suggest that's a good way to do it. Okay. So I need somebody to help me out and take 12,111,009 and reduce it mod 29. And no, I don't have the answer. So, be a little careful. How do you do that, by the way? What do you do to reduce it mod 29 on a calculator? If you don't have a fancy button. Assume you don't have any fancy buttons. Divide by 29. Okay, so exactly. You take this number and divide it by 29. You get some awful decimal, probably. Truncate, actually, so.
Oh, so I have to do it.
Oh, is it a whole number?
No, it isn't.
Oh, no.
Oh, wait, 29.
Oh, it is a whole number. So, in other words, this is congruent to 0 mod 29. It goes into 29. Well, that was easy.
For,
Okay, so if we call this whole thing x, just give the whole thing a name, we'll call it x, then what we've already figured out is that x is congruent to 0 mod 29. Okay, so x.
For 149.
Actually, that's an important thing to. No, I'll come back to that. Okay, so now we got to do 149. Let's do 149.
You get 140 or negative 9.
For this thing? Okay,
Yeah.
So, oh, and
And
this
then
is.
raised to the
Oh, I'm sorry. I want
Forever
x
power.
to be. X is this whole power here.
Yeah.
Right. So this part alone is 0, and then 12,111,009. If you divide, so here's what you do with a simple calculator. You divide by 149. You figure out what the quotient is, how many times 149 goes into here. You forget about the remainder. And then what you do is you subtract. So however many whole numbers of times 149 goes into this number, so let me just do it. Yeah, so this thing is it turns out, this number, 12111,009, is 149 times, and then what it is it's 81,281.3 something something something. So what you then do is you take this number and you subtract 149 times 81,281, and that will leave you with the remainder, which will be something that is less than what you divided by. Right,
you get
and so what did you end up getting?
140?
140, which is the same thing as negative 9 mod 149.
I'll need to raise it all to the 8, 7.
And we're going to have to, I haven't been looking at the exponent yet.
Oh,
So,
Did you also take the decimal part and multiply by 149? Take the decimal part and just multiply that by 149?
huh?
That would give you something like
Yeah, that's essentially the same thing, right. Yeah. Okay. Okay, so we're trying to figure this thing out. We know that, so x is certainly congruent to 0 to the 8765, which is 0 mod 29. You know that. And then x is also congruent to negative 9 to the 8765 mod 149. Right? So how are you going to figure this thing out? You want to use Fermat's little theorem, right? Because you're computing a large power of a number. And 149 is prime, so what that means is